In our next section here, let's take a look at the check your understanding questions, once again focusing on conservation of energy. Question 1. At the library, a 0.5 kilogram book, starting from rest, slides down a 1.5 meter long slope into a book bin. The height of the ramp is 0.84 meters. The force of friction acting on the book is 2.0 newtons. And we are asked to find the thermal energy produced and the book's kinetic energy at the end of the slope. Once again, I'm going to start by identifying my variables right away. So I have the mass of the book is 0.50 kilograms. I know the length of my ramp, or the length of my slope, is going to be 1.5 meters. So that's going to be my displacement, 1.5 meters. I know the height of the ramp is 0.84 meters, and the force of friction acting on the book, so force of friction, is 2.0 newtons. And we are asked to find the thermal energy produced. So basically, we just need an energy equation that uses the information that we have, and we want the friction produced, or the thermal energy is going to be produced just by the friction. So if we just have the ball or the book dropping or whatever, there's no thermal energy really involved until it squishes at the end, and then the compression will heat up the ball. That's a more complicated situation. If we just had the book dropping and not really deforming, there's not really going to be any thermal energy to consider. But think about if we rub our hands together. Here's my terrible, creepy hands rubbing together. We know that that creates friction. The same thing's going to happen when the book slides down the ramp. So we're just going to worry about the frictional force here, and we're going to use this equation. Energy, thermal energy, is going to be force times displacement. So I know the force of friction was 2 newtons. I know it was exerted over a distance of 1.5 meters. That was the length of the ramp slope. And so 2 times 1.5 is just going to be 3.0 joules, and that's it. That's our thermal energy here. So basically all the frictional energy is being converted into heat as the book is sliding. And that's true in a lot of cases. Some of you talked about this in earlier work as well, that if we have like a vehicle driving and we hit the brakes to slow down, think about we have all that kinetic energy from moving quickly, and then we come to a stop at the stoplight. Where did that energy go? That energy actually got transferred to the rotors through the brake pads and into the rotors through the force of friction, and then it's dissipated as heat. So that's why if you were to stop and like put your hand behind your tires and touch your rotor, or sometimes you can even feel it on the wheel hub or whatever, it's very hot, and that's because all your energy of motion, your kinetic energy, got converted into thermal energy. All right, let's take a look at question B. Find the book's kinetic energy at the end of the slope. In order to do this, we want to consider the book's total energy at the top of the slope and the book's total energy at the bottom of the slope. So I'm just going to kind of box this off to keep it separate, and let's take a look. So we're going to talk about energy total 1, and that's when the book is at the top of the ramp, and energy total 2 when the book is at the bottom of the ramp. And I know that energy can either be created or destroyed, so overall, the energy at the top it has at the top of the ramp and the energy it has at the bottom of the ramp are going to be equal. I know that at the top of the slope, there's 2 possible contributions to the energy. That's going to be the kinetic energy, so the energy of motion, and that's going to be the gravitational potential energy. When we reach the bottom of the ramp, we're going to once again have kinetic energy, potentially kinetic energy. We are going to have the gravitational potential energy, and we're also going to have to deal with the thermal energy because the book has heated up from the force of friction. All right, let's deal with these pieces one at a time. First of all, the kinetic energy at the top of the ramp. We haven't released the book yet. It's just sitting at the top of the slope. So we know that the velocity is going to be 0, which means the value here is going to be 0. The gravitational potential energy we're going to find using the formula mgh. We're going to label that h1 because that's going to be our initial height. We can pretty safely assume that the book is moving when it reaches the bottom of the ramp, and so we are going to have some value for our kinetic energy, half mv squared. At the bottom of the ramp, I know I have no height left, so the gravitational potential energy is going to go to 0. And the thermal energy we already calculated, so I can just put that in as 3.0. Alright, let's go through again, and let's find some more values. The gravitational potential energy at the top, well, I know the book has a mass, checking back here at our variables, a mass of 0.5 kilograms. Force of gravity is 9.8, and the height of the ramp was 0.84 equals. Now, I don't know how fast my book is moving, but that's okay. I can actually figure that out separately in a moment. So I wrote this to show the equation. We don't actually need it. I'm going to leave this as just our kinetic energy 2, and then we're going to add in our thermal energy. And remember, the question asked us to find the kinetic energy. Kinetic energy is the only variable I have left now. All I need to do is rearrange this equation and simplify, and I'm done. So let's start by simplifying a little bit. I'm going to multiply these pieces together, find the product. So 0.5 times 9.8 times 0.84 is going to be, I'm going to carry some extra decimals through for now, 4.116 equals, equals EK2 plus 3. Rearrange and solve for EK2 is equal to 4.116 minus 3.0. EK2 is going to be equal to 1.11 joules. And that's it. The question just asked us to find the kinetic energy. We could take it one step further and find the velocity, but we don't need to. All right, next up, let's take a look at question number 2. We are told that there is an 1100 kilogram roller coaster, including all passengers, that starts from a slow speed of 2 meters per second at point A. So let's record that. So initial velocity is 2 meters per second, and that's occurring here at point A at the top of the track, on a frictionless track as shown in the diagram below. Question A asks us, where will it have the maximum speed, and what is the maximum speed? The first thing I want to notice is that the roller coaster is going to have the most speed when it has the most kinetic energy. We've seen in our work here already, and I'm going to make a little sketch here, gravitational potential, kinetic energy, and that is, as I descend from a height, my gravitational potential energy is going to decrease, and as I descend from a height, my kinetic energy is going to increase. So the kinetic energy will be greatest, the speed will be greatest when the gravitational potential is lowest, which is to say the lowest point on our ride is going to be the point where we have the greatest kinetic energy and the greatest speed. I'm just going to move this off to the side here. We'll refer back to it later if we need to. So when will it have maximum speed? Well, at the lowest point on the roller coaster, so therefore at point D. So let's just kind of jot that down. Max speed at point D. And I don't have a lot of room to write here, so I'll say a little bit more than I'm going to write. So it's going to occur at point D because that is the place where the gravitational potential energy is lowest, which means that energy has been transformed into kinetic energy, and therefore that is when the kinetic energy is highest, and therefore it must have the greatest velocity at that point. What is that maximum speed? Since we're dealing with speed, we have a hint right away that we're going to need our kinetic energy equation in order to find the velocity. But basically, we want to think of this in terms of energy. So we're going to start kind of like the previous question by considering the fact that the energy at point A is equal to the energy at point D. And so we're going to find our total energies, find all our variables, rearrange and solve for kinetic energy, and then finally for velocity. So the energy at point A is equal to the energy at point D. At point A, we're dealing with gravitational potential energy and kinetic energy. And at point D, we are once again also dealing with kinetic energy and gravitational potential energy. I am not going to have enough room here, so I'm going to create a new page and jump to that for a moment. Alright, so on our new page, we're going to repeat that. We're going to say that the total energy, we're going to say that our total energy at point A is equal to our total energy at point D. We're going to add up the gravitational potential and kinetic energy at each of those points. So gravitational potential at point A plus kinetic energy at point A is equal to gravitational energy at point D plus kinetic energy at point D. Let's use we're trying to find our kinetic energy at point D. Well, we're trying to find the max speed. We're going to find the kinetic energy first. So we're going to leave this as a variable, but we're going to represent the rest in an alternate form using their formulas. So I'm going to have my gravitational potential energy, A, plus my kinetic energy, half mv squared, equals gravitational potential energy at point D, mgh at D, plus kinetic energy at D. And I know these values, so let's plug them in. The mass of the roller coaster is 1,100 kilograms. Force of gravity is 9.8. The height of the roller coaster at point A was 14.5 meters. Plus the velocity at the beginning, or our kinetic energy at the beginning, is half m. We know the velocity, or the mass, is 1,100 kilograms. And we were told that the velocity was 2 meters per second squared. Equals, and once again, mass is 1,100, gravity is 9.8, height at point D is 5.2 meters, plus our kinetic energy at point D. Now we're just going to simplify, rearrange, and solve so that everything is equal to EK, or kinetic energy at point D. So once again, the answers are given on Brightspace, but I'm going to recalculate them myself to make sure we are correct. So our first chunk here is 156,310 joules plus half times 1,100 times 2 squared is 2,200 equals 1,100 times 9.8 times 5.2 is 56,056 plus our kinetic energy at point D. I'm going to kind of skip a step here just to save time and space, but I think we all know how to add numbers and rearrange as needed. So 56,056 minus 156,310 plus 2,200 is going to give us a value of 102,454 joules. And it looks like there actually is a mistake in the answer key on Brightspace. I think it's just a typo. I've double-checked my answer and I'm confident with it, so I'm going to continue. The answers will still be very close. They're only off by 200 joules, but if you notice they're different, that's why. All right, we found our kinetic energy. That's great, but we were asked to find the velocity, or the speed. So always make sure you go back and look at what the question is actually asking. You don't want to do a whole bunch of calculations and then never actually clearly state your final answer. So, using this value, I'm going to use my kinetic energy formula. Energy kinetic is half mv squared. We've already rearranged and solved previously, so we saw that velocity is equal to 2 times the energy divided by the mass. So let's plug in our values. 2 times 102,454 divided by mass was 1,100 kilograms. Is going to give us a value of times 2 divided by 1,100 square root. So our velocity at point D is going to be equal to 13.6 meters per second. And if you're interested, that's equal to about 49 kilometers per hour. So the question asked us, once again, double check the question, make sure we answered it. Where will it have the maximum speed, and what is the maximum speed? So, therefore, let's have our concluding statement. Therefore, maximum speed is 13.6 meters per second at point D, where kinetic energy is maximized and gravitational potential energy is minimized. but I'm not going to write all that just to save time and space. Next up, we have question B, which asks us, what is the roller coaster's final speed, or speed at the final point of h? Let's get a new page and start that. So let's look at our variables. Just because I started a new page, it's not as easy to refer back to them. That's okay. So we're going to have a mass of 1,100 kilograms. We are going to have an initial velocity at point A of 2 meters per second. We know that the height at point H was 14.5 meters, or the height at point A, and the height at our final point H is going to be 8.3 meters. Once again, we're dealing with this in terms of energy. That's the whole point. And so we're just going to compare the energy between point A and point H. Remember that the track is frictionless, so we aren't losing any energy along the way to air resistance or the track or whatever. So we know in each point that we're going to deal with the kinetic energy and the gravitational energy and the kinetic energy and the gravitational energy. Now we do have one advantage here. We've already found the sum of the energies, or the total energy at point A, in our question A. So this is question B. This was question A. And so if we take a look, our total kinetic, or our total energy here at point A is going to be, I didn't actually find the total here, but we can add that up really quick once again. 156,310 plus 2,200. So our total energy, I'm not going to show all my work here because we already did it previously, is going to be 158,510. Once again, there's a slightly different answer, or there's like a mistake in the question. It says that the initial energy is 178,310 joules. That's not correct, but we do have the correct number here, and they did use the correct number in the calculations on Brightspace. So just if you're checking and comparing and wondering why I'm writing some things that are different, that's why. All right. As for point H, we are trying to figure out the velocity, so I'm going to leave my kinetic energy formula the way it is for now, and then we'll deal with our potential energy. I can rearrange right away. So EKH is equal to 158,510 minus MGH at point H. Let's plug in our values. Mass was 1,100 kilograms, gravity was 9.8, and the height at point H was 8.3. So let's calculate. Minus 1,100 times 9.8 times 8.3 should give us a value of 69,036 joules. As before, we're going to use our velocity equation. 2 times the energy over the mass equals 2 times 69,036 divided by the mass, which was 1,100. Don't forget the square root. And we're going to find that our velocity is, divided by 1,100, square root, 11.2 at point H is 11.2 meters per second. And I'm not going to make a concluding statement just for the sake of time, but we've kind of stated it pretty clearly there at the end. Final question C. What constant braking force would have to be applied to the roller coaster at point H to bring it to rest in a horizontal distance of 5 meters? All right, I'm going to work here, and let's list our variables and then dive into it. So we know that the total energy in our system at this point, because the total energy at one point is the total energy at any point. So our total energy is going to be at any point. I was at point A, now at point H because it doesn't lose any along the way, is 158,510 joules. I know the mass of the cart is 11, or the roller coaster is 1,100 kilograms. I know the gravitational energy at this point is, that's this piece here, I just didn't calculate it separately, so 1,100 times 9.8 times 8.3, 89,474 joules. And I know the kinetic energy at this point is 69,036 joules. I'm just going to double check that really quick. Plus 69036. Yes, looks good. So these two sum to equal this. So that's correct. Once again, the answer key is different numbers, but I'm confident in my answer, so I think they made a mistake and used the wrong value at one point. If it turns out I'm wrong, let me know, but I don't think so. And the distance, displacement, because we want a braking distance of 5.0 meters. And we're trying to figure out what is the frictional force that we need. Well, we already talked about in our thermal energy equation and stuff in the first question that energy can be expressed as force times displacement. So work is force times displacement. Work is just a change in energy. We're changing the energy of certain parts, or we're changing certain parts of our energy. So we're going to use the equation where energy is equal to F times delta D. So let's think about it this way. We aren't dealing with our gravitational potential energy. We're just canceling out the kinetic energy. So the kinetic energy of our system is what we're going to get rid of. And so it's all going to transfer into thermal energy. So our thermal energy is going to equal our total kinetic energy at this point, which is 69,036 joules. We know that our thermal energy equation is just force of friction, force of kinetic friction, because we're moving, times delta D, and I basically know all those values. So let's rearrange before we substitute. So we're trying to solve our force for the braking distance. So our force of kinetic friction applied is going to be our thermal energy divided by delta D. Let's plug in our numbers. Our energy was 69,036. Our distance we were given was 5. So 69036 divided by 5 gives us an answer of 13,807.2. Looks good to me. Now, we do have too many digits here. We only have two significant figures here, so I'm going to have to express this as two significant figures. Some of us are forgetting this in our writing, so watch out for this. So we're going to express this as, basically we want two digits, so 1.4 times 10 to the power of 1, 2, 3, 4. Or we can express it as 14 kilonewtons. And once again, what are we trying to find here? What actually is this value? The question said, what constant braking force would have to be applied to the roller coaster? So what is the amount of kinetic friction we need to apply to stop this? And this is what it's going to be, our 14 kilonewtons, or 1.4 times 10 to the 4 newtons. So therefore, let's make a concluding statement. Therefore, the braking force of 1.4 times 10 to the power 4 newtons is required.